Good morning to all of you. My name is Pubudu Wijesinghe. I'm a student at Levy Lab at University of Pittsburgh. My project is single-photon detection from gated nanostructures. This project is carried on with the help of collaborators from University of Wisconsin-Madison. So I would like to start by thanking our collaborators and the funding agencies mentioned here. Single-photon detection is a crucial technique in optics and quantum mechanics that allows for precise measurements of light at low intensities, and it has various applications in fields such as quantum imaging, LiDAR, and quantum computing. Also, it enables the study of fundamental physics by investigating the behavior of single photons in complex systems. One of our experiments is focused on developing a platform based on optics for molecular scale nonlinear spectroscopy, which can be utilized to probe different materials along with their properties. Furthermore, combining this with a single photon detection platform, we can effectively probe gated nanostructures such as graphene nanoribbons, and also any other van der Waals system. However, in this work, my primary focus is to probe gated graphene nanostructures via some frequency generation spectroscopy. The platform that we use to create these nanostructures is the lanthanum aluminate strontium titanate heterostructure, which is also abbreviated as LAOSTO, which exhibits several interesting physical phenomena. In this work, we are exploiting certain properties of this to effectively use it as a spectrometer, which I will be explaining how in the next few slides. The figure shown here on the left demonstrates the unique lithography technique we have developed based on conductive atomic force microscopy. This can induce an insulator to metal transition on an LAO-STO interface. We use LAO grown at the critical thickness on top of STO and then use an AFM tip to write nanostructures on top of LAO. While we are writing, when we bias this tip with a positive voltage, it attracts electrons from the STO to the heterostructure interface, making the regions conductive. And by biasing this tip with a negative voltage, we can effectively erase the structures that we've created, restoring them back to the insulated state. So this whole procedure allows us to use this interface as a canvas on which we can design nanostructures. Our group has shown that these smallest feature size of these nanostructures can be as low as 2 nanometers in size at room temperature, and also this process is reversible and reconfigurable. So you can see, using this lithography technique, we can create a whole class of different nanostructures with different materials. These two papers from our group marked the foundation of this platform, which show that these junctions constitute both nanoscale photodetectors and nanoscale nonlinear generators, and also detectors. Figure A here shows a device we have created using the lithography technique we have discussed previously. These yellow objects denote gold electrodes, and the green wires denote conductive nanowires. There are two terminals to act as a source and a drain. Also, in the nanowire connecting these two electrodes, there's a gap in the order of 10 nanometers, which acts as a source, acts as a nanojunction in our experiment. As shown in figure B, when focused laser light overlaps with the device, there is a sharp increase in the photocurrent. The response is highly localized in space. By measuring the generated photovoltage as a function of the coordinate of the focused laser spot, you can see a scanning photovoltage microscopy image generated on figure C. The scanning image reveals a strong localized photovoltage response at the site of the nanojunction. This photoconductive response is electric field tunable and spans the visible to near infrared regime. Shown here is an experiment which shows that this 4-terminal structure has the ability to generate or detect terahertz signals at the nanoscale. We would measure delta V versus the time delay between two ultra-fast pulses. This experiment has shown that this junction acts as a nonlinear generator and a detector. Now that we have discussed about our platform, next I'll go on to explain our experimental setup that we use to conduct these time domain experiments. This consists of two parts: an optical control setup, then leads to a transport measurement setup. Within the optical part, we start with a titanium sapphire ultra short pulse laser, which then goes onto a homemade pulse shaper. This pulse shaper has the ability to change the phase and amplitude of the pulse accordingly to compensate for any aberrations that the beam might go through in its way. Then the beam goes onto a Michelson interferometer setup, which is also home built. You can see we have two arms split by the 50-50 beam splitter, one as the main path, and using the stage attached to the other path, we can control the time delay for our pulses. Then they recombine at the beam splitter again, goes through to the device through a 100x microscope. We can control the DC bias and look at the differential voltage generated at the nanojunction as a function of tau, which is the time delay. In this experiment, we use graphene to probe its properties using this technique, since graphene has some interesting optical properties, and also since it opens up the possibilities to be used in many applications in the field of nanoelectronics. This slide shows the different nanostructures we hope to use in this experiment. The figure on the left shows the top view of graphene on top of a LaOSTO heterostructure, and on the figure on the right demonstrates graphene nanoribbons on top of a LaOSTO device that we have created. This is a 4-terminal nanojunction with a dedicated nanowire to control the side gate. You can see the graphene nanoribbons cluster constrained within the nanojunction. Here we have a sample time domain signal from one of our experiments using the graphene LaOSTO sample shown on figure A. Figure B shows the delta V versus the time delay directly measured from our setup. On the right is the corresponding power spectrum of figure B, which gives us three interesting features to look at. There's the linear response from the visible to near infrared input frequencies, and on either sides of that we get the sum frequency and the difference frequency generated from this nonlinearity of the sample, as we discussed earlier. It is possible to generate sum and difference frequencies even without graphene using our LaOSTO platform due to its own nonlinearity. So why are we interested in graphene? The motivation to use graphene is because we've got even more interesting results through the graphene and LaOSTO structure, like high harmonic generation. Figures B and C are extracts from an experiment from our group about gate-dependent extinction features of graphene, which proved to be an important result for the next experiment. Then in a follow-up experiment about high harmonic generation, time domain photovoltage measurements were performed on a similar graphene device excited by ultra-fast visible to near infrared laser pulses at low temperature. In this occasion, it has revealed a gate-tunable extreme ultraviolet high harmonic generation response with both even and odd integer harmonics. Looking at this result, the second harmonic shown here should correspond to blue light. So you can see we have already measured the blue light coming out interferometrically. The next step would be to measure this light in the far field. One of the frequently asked questions about this is how much light is actually coming out from this. To answer this, there should be a direct observation of the light generated via this nonlinear response in the far field. This further allows us to verify the results of this high harmonic generation experiment and also to effectively calibrate our nanojunction detector. Although these light pulses should be at an energy of nearly 3 electron volts as mentioned, which should be visible as blue to violet light, this second harmonic response from the nanojunctions has extremely low intensities, making it challenging to detect it. We have already tried detecting it with an APD at room temperature, which proved to be unsuccessful. So right now we are in the process of designing this single photon detection scheme for experiment. There is a long pass dichroic mirror which has a cut-on at 650 nanometers, and by replacing this APD, we use a cooled photomultiplier tube hybrid detector which is compatible with time correlated single photon counting. In comparison to the previous APD setup, here we have two major advantages. One is, since this is a photomultiplier tube detector, the sensitivity for second harmonic response of near infrared wavelengths will be higher while cutting off the near infrared wavelengths, which will make it easier to detect our wavelength range. Other advantages, since we are using a TC-SPC system, we can further increase the detection limit by synchronizing it with our light source. Hence, using this setup, while we can generate terahertz signals at the nanojunction, we can also look at and directly measure the generated optical response from the device by monitoring the reflection. I should mention the actual experiment has not been performed yet due to some supply chain issues of instruments. We are still in the alignment and calibration stage. However, we do hope to achieve positive results in the near future. In summary, using our platform, we can probe nonlinear optical properties of different systems. These measurements are interferometric electronic measurements. In this experiment, we try to detect the second harmonic generation generated response from graphene at the far field, and it will eventually act as a mechanism to calibrate and verify a nanojunction detector. In addition, this single photon detection platform enables us to probe more and more complex systems. Here's a group picture of a group. Thank you very much for listening to my talk.